My name is Virendra Jha from Canadian Space Agency. I'm the organizer of this plenary. I'll be introducing the panel members. First of all, on my extreme right is Dr. Richard Lawford. He's currently working on contracts with World Health Organizations and JAXA and University of Texas. He's the chair of Global Earth Observing Group, GEO, Integrated Water Cycle Observation Team, and he's also a member of the Committee for Global Water System Project. And previously, he has experience of working both at NOAA and NASA. Next to him is Dr. Hegde. Dr. Hegde has been with Indian Space Research Organization since 1975. Since 2011, he has been chairman and managing director of Antrix Corporation, which actually looks after the commercial space activities for the Department of Space in India. Dr. Hegde has published over 60 technical papers, and to his achievement, he has been recognized with ISRO's Performance Excellence Award, ISRO Team Excellence Award, and many other honors related to telemedicine, disaster management, and World Mapping Award. He is also the Vice President of International Astronautics Federation since 2010. He's a fellow of Astronautical Society of India, member of IAA, International Academy of Astronautics, and member of the Indian Remote Sensing Society. And our moderator today is Robert Sanford. Robert is the chair of UN Water for Life Decade Canada. He's the director of Western Watershed Research Collaborative work in Canada, and he's a senior policy advisor for Interaction Council, which actually is a group consisting of 40 previous heads of state who are all concerned about water. Then we have Dr. James Famigliati. He's the senior water cycle scientist at NASA Jet Propulsion Lab, and he's the leader of JPL Water Initiative. He's also a professor of Earth Systems at University of California, Irvine. He and his research team use satellite to develop computer models to track water availability on Earth. And finally, to my right is Mr. Jim Crocker. Jim is currently Vice President and General Manager of Civil Space with Lockheed Martin Space Systems in Denver, Colorado. He has been a leader in advancing astronomical systems and investigations in a number of leading scientific organizations such as Ball Aerospace, Johns Hopkins University, European Southern Observatory. He is a recognized world leader for his successes in leading and managing astronomical projects involving cameras such as Sloan Digital Sky Survey and the COSTAR, which went on the Hubble telescope. So over to Robert Ranford, who will be moderating, and enjoy. And if you have any questions, there will be someone with the paper, so please write your questions, which will be given to the panel. Thank you.
Well, thank you very much for the kind introduction. It's a great honor to be invited to moderate this panel. There are grave concerns around the world that we may be heading for a global water crisis. Growing populations, expanding agricultural demand, and rapid industrial growth associated with development all demand more water at a time when supply is becoming less and less reliable due to warming-induced changes in the rate and the manner in which water moves through the hydrologic cycle. At the same time, disappearing Arctic sea ice and changes in the timing, duration, and extent of snowfall in the Northern Hemisphere appear to be altering the behavior of the jet stream, causing destabilization of historic weather patterns, which in combination with a poleward advancement of tropical storm tracks and a warmer atmosphere's capacity to carry more water vapor appears to be resulting in more extreme weather events. Flooding events are damaging expensive critical infrastructure widely, while at the same time, and sometimes in the same region, deep and persistent drought threatens agricultural productivity. Satellite-based technology is our best bet for understanding the linked ocean, land, life, water, weather, climate system that finds its ultimate expression in the global hydrologic cycle. From space, we can see and forecast changes in weather patterns, track and predict precipitation, forecast water availability, stream flow, and soil moisture, monitor groundwater depletion, plot and predict processes of desertification, and also identify contamination pathways as well as red zones and dead zones and their effects. But perhaps more vitally, satellite observations are for the first time permitting us to anticipate seasonal and longer-term trends in hydroclimatic conditions and their consequences. But as we're about to find out, these bold technologies do come with their own set of very diverse challenges. And we have on this panel 4 of the world's leading experts on the subject of how space assets help provide water for all. Now, our experts have already been introduced to you. Each will in turn speak for 7 minutes, and then I will ask the panel a few questions on matters related to their observations, and then open questioning to the audience before offering concluding remarks on what's said. So to begin, on the subject of what makes satellite imagery different and critically important to our understanding of the Earth system and our future is Lockheed Martin's James Crocker.
Well, thank you so much. You know, there are things that we've often thought through history that were wrong. One of the first things is that you might hear is that the Earth was flat. We know that's not true. And then we, for thousands of years, believed that the Earth was the center of the solar system. And we, of course, know that's not true today as well. The other thing that we believe is that the Earth is a water planet. You see the Earth from space, and it's predominantly covered by water, salt water mostly, of course, but that it's a water planet and covered with water. But the truth of the matter is actually quite different. If you take an apple and you drop it into a glass of water and you take the apple out, the amount of water held by surface tension on the apple is about the amount of water that's on the surface of the Earth. The Earth is actually very, very, very dry. As a matter of fact, we know another planet that falls into that category, and that's, of course, Mars. Mars, we know, and as a matter of fact, we just sent a spacecraft to Mars called Maven, and let's see. We sent a spacecraft to Mars called Maven that's actually trying to find out what happened to the water on Mars. We know it lost its atmosphere, and as a result of that, the water went away. And so now when the rovers, satellites from orbit or rovers on the ground look at Mars, they see a very dry and desolate planet. But the truth of the matter is there wasn't a lot of water there to begin with when you think about the fact that the oceans of the Earth are really just the water held onto the core of an apple by surface tension. So we've really have a long history now going back to the launch of the first environmental weather satellite, TIROS-1, in 1960. And one of the interesting things from this New York Times article is actually how that was such a revelation. The press picked up on it right away that from above the atmosphere, you could actually see the Earth in new and very, very different ways. Just most recently, to bring it back 25 years ago to a story in 1987, basically from a satellite, polar orbiting satellite built by Lockheed Martin for NOAA, the POSE satellite, we actually saw images come back that showed warm currents that were moving into the North Carolina estuaries and bays that actually were beginning to kill the shellfish, and tens of millions of dollars of economic value began to be lost. And it was only by using satellite data that they were able to understand that these warm currents were actually coming up from Florida, being carried by the Gulf Stream. It was a very unusual event, had not been seen or noticed before. And from that, NOAA actually put in place something called Coast Watch, which basically then began to give high-resolution imaging on a periodic basis to allow us to watch for these types of events. And over the years, NOAA added many images and types of data, from ocean color to turbidity to add to the information and data. And so now this is continuing to this day to be one of the important elements in our ability to understand water. Now, of course, this is an example of an ocean event, but let me just bring you to more recent times. This year in August, in the city of Toledo, just a few hundred kilometers from here, there was another algae bloom with 4 very toxic types of algae. Their Latin names very difficult to pronounce, so they were called Annie, Franny, and Mike, 3 different very toxic algae that, because of their toxicity, it put a city of almost 500,000 people without fresh drinking water. And NOAA upped the frequency that they did the monitoring and from satellites and provided that data to allow people to respond and to understand what was coming from these algae blooms. So moving from coastal waters now to freshwater with the same type of data. That's just one example of what satellites have been able to do from space over the last 50 years. They've become more and more accurate, they've become more and more timely, and every day the launch of the Sentinel satellite by the Europeans will allow us to look at freshwater resources on a more periodic basis. Satellites give us not only the timeliness of the data, but the ability to look and see things that change. Freshwater is not just about lakes, it's not just about underground aquifers, it's also about the ability to predict rainfall, the ability to track, such as the satellite Landsat, which Lockheed Martin has a 40-year history of. The Landsat satellite is able to track the estuaries, it's able to track freshwater supplies, and routinely and over long periods of time. And as we get more and more satellites and more international involvements of the satellites, we're able to extend that further and further. New instruments are coming on board satellites that just even further increase our ability, and some of them perhaps weren't obvious, at least to many of us, in how they might be used. The GRACE satellite, for example, the Gravity and Climate Experiment satellite, has been able to determine that in the Colorado River Basin over the last 10 years, we've lost 65,000 kilometers of fresh water, which is an area the size of Lake Mead. And so we are able to, with satellites, continue to monitor and improve monitoring of water, of weather, of climate, but more importantly, of fresh water and its availability for our citizens around the globe. You know, it's very interesting. There was a quote I found by Socrates that said, "Man must rise above the earth, he must rise above the atmosphere and even beyond in order to understand the world in which he lives." And that's certainly what we're doing today with satellites and our ability to monitor water globally, worldwide, and more accurately and with greater precision into the future.
Thank you very much, Jim. And further on the subject of Earth observations, Dr. Jay Famnietti.
Thank you very much. Can you can hear me okay? Thank you. And thank you, Jim. I wondered why that apple was there, and now I know the answer. Can I get my slides? Thank you. So I am a hydrologist, and in my research group, we use satellites to track changing freshwater availability on land. And in particular, we are very focused on groundwater. And because of its importance to regional water supplies. About a third of the world's water use comes from groundwater. Over half of the water that we use for irrigation is from groundwater. It is the strategic reserve in times of drought. Right now, in California, we're in the midst of this epic multi-year drought, and we're getting about 75% of our water from groundwater. And groundwater, by definition, is the water that's under the ground, stored in soils or rock units called aquifers, rather than rivers and lakes on the surface. So a robust, sustainable groundwater reserve is the key to water security in many parts of the world. But in many parts of the world, groundwater really goes unmanaged and is poorly monitored relative to the more visible rivers, water in rivers and reservoirs. My team works quite a bit with the GRACE mission, which stands for Gravity, Recovery, and Climate Experiment. And Jim, that Colorado River Basin paper is actually one from our group. GRACE measures tiny variations in Earth's gravity field that result from the movement of water around the globe. In short, GRACE really functions like a scale in the sky that weighs the amount of water moving into or out of a region because of, say, a big snowstorm or a flood, or due to drought, or due to groundwater depletion. And I'll focus on the latter. And in particular, what GRACE has shown us about groundwater depletion and some of the traction that we've gotten with policymakers. So the drought situation in California is absolutely abysmal. There's been no rain or snow melt for a few years now, and there's no end to the drought in sight. More towns each day are running out of water. More and more farmers are throwing in the towel, and that's really important because California supplies food not only for California but for the nation, for North America, and really all around the world. So here's what some of our GRACE data look like, and this is a chart that shows the ups and downs of water storage in the combined Sacramento and San Joaquin River basins, which are shown in the inset. That's really where all the water is in California. And so these ups and downs are due to wet season, dry season. We're looking at monthly data from about 2003 through right up until, almost up until the present. So what's very interesting about these data is that they show all of the water stored in the river basins. Okay? All of the surface water, all of the soil moisture, all of the snow, all of the groundwater. There is no other way to capture and understand data like this. There's no way to do it except by using the GRACE mission. And so we can see a few key things. We can see the recent drought that declined over the last 3 years. We can see that the low point in November 2013 was the driest dry season in the lifetime of the mission. We can see that our most recent wet season, that little bump all the way over on the right, that's the last winter of 2013. That doesn't even rise to the level of the previous dry seasons. It's drier than just about all the previous dry seasons. Just to share some numbers with you, over the last 3 years, those basins have lost 15 cubic kilometers of water each year. That's you can choose your favorite units. That's 12 million acre feet. That's 4 trillion gallons. That is more water than all 38 million Californians use each year for domestic and municipal water use, so everything that's not agriculture. And we can also see that the drought really has many timescales. We talk about it being a 3-year drought, but if we look back to about 2005, that first big peak, maybe the drought's been going back that far, or really that whole time series shows a sort of steady decline. So we see multiple timescales of drought embedded in these data that we don't otherwise see from other data sources. And then just some imagery there shows the progressive drying of the dry season. So those figures getting wetter and wetter. Now, how much of this is groundwater? Turns out about 50% of the water storage changes that we see there are from groundwater. And to put it in perspective, let's look at this chart that combines USGS data, shown in red, and the GRACE data, shown in green, for cumulative groundwater depletion in the Central Valley, the big agricultural region in the central part of the state. So what we see here is so it's cumulative groundwater depletion on an annual basis, starting arbitrarily at 1962, going up until the present. The colors in the background represent whether it's a wet season or a dry season. So the dark blue is very wet, the white is a drought, and those lighter colors are sort of moderately wet and moderately dry. And so one of the things that's very clear is our pattern of groundwater use, and we see this repeated all over the world, that during wet periods we get a little bit of recovery, but then in droughts we get huge declines, right? Huge groundwater use. A little bit of recovery, big decline. Okay, so we're clearly using more water than is being replenished. It's practically the definition of unsustainable. The picture doesn't get any better when we look nationally. The blues in this figure, we're showing trends in water storage. Blue is gaining water, red is losing water. We see a lot of hot spots in the southern US, but in particular, our two big food growing regions, the Central Valley and the Southern High Plains Aquifer. And it also doesn't get any better when we look globally. This is a global map, and again, same color scheme. Blue is gaining and red is losing, and these charts are for the major aquifers around the world in the arid and semi-arid, arid and semi-arid parts of the world. Just about all these aquifers are being depleted at a pretty rapid clip. Okay, so I want to make some comments about policy. We are making progress. In fact, this is this week's cover of Science, and this is out right now. And this is an image from our group for California, and this supports an editorial from Marcia McNutt, who just wrote an editorial on drought and groundwater depletion. So we're hitting it at a pretty high level. For those of you who don't know, Marcia McNutt is the chief editor of Science, but also former director of the USGS and former president of the American Geophysical Union. And I have one more slide. Just last week, Governor Brown signed some historic groundwater management legislation. Our groundwater was unmanaged until last week. And so we'd like to think that some of our satellite work has had an impact on that. And it has, but it's been a lot of work. It doesn't just happen. So I just want to finish up by saying that those of us who do this sort of work and have access to this sort of imagery and understanding also have a responsibility to communicate it. And so in my group, we've made a Herculean effort, really, in Congress, to the state. I've given hundreds of lectures, public talks, op-eds, blog posts, social media. So let me finish my comments by saying that satellites have a huge role to play, and can contribute to understanding the global water crisis, but it has to go beyond just us publishing our papers in scientific journals. We do have to communicate the science and I think we have a responsibility to communicate that science to the general public, but also to decision makers and to resource managers. Thank you.
On the topic of freshwater for all in India, Dr. V.S. Hegde.
Thank you. Distinguished colleagues, let me share some of the examples as to how we have used space assets for managing our water resources in India. See, basically, our applications, whatever we have developed in India and put to use, across the country, is based on the national imperatives. See, we have 2% of world's geographical area, 4% of world's water resources, but 17% of world's population, also large cattle population. And of course, I don't want to run through the total statistics. Though we are among the 10 top water-rich countries in the world, the water quality and per capita availability is not all that good. The agriculture in India is predominantly rain-fed, but much area is degraded. Our very good rainfall of about 1,100 millimeters annually happens actually in 5 to 150 days. Danger of being close to tropics. We don't have the luxury of temperate climate. And that too, many a times, the total rainfall happens in just 100 hours. So due to this, we have to innovatively, carefully manage our water to provide drinking water, to ensure our food security, our agriculture security. Over the years, we have developed a lot of applications to manage our water resources. We monitor irrigation infrastructure. Incidentally, in the Asian region, we are only next to China, having gone in for large number of irrigation projects, over 100 major projects. So operational hydrological services we provide. We have a complete inventory of glaciers, snow accumulation, snow melt runoff, because many of our rivers in northern part of India are fed through glacier melt. We do water resources assessment basin-wise, and of course, you just name it, that kind of application we have developed and put to use in India. Don't get much scared. See, 1986, India went through tremendous drought situation. In fact, two of my colleagues with whom I worked are also here. This is from Western India. You see one well having water and people carry home drinking water miles away. And we have just come out of the situation thanks to innovative space application or space data application. We got into preparing hydrogeomorphological maps. I mean to say, map the landforms and assess each landform in terms of lithology, structural features, the weathering characteristics, soil, slope, so indirectly assess the groundwater prospects to drill a borewell or to recharge a defunct borewell or to put recharge structures. And now we have gone further ahead. We are trying to empower Gram Panchayats, we call. That is, India is divided into something like 250,000 smallest administrative units, the lowest administrative units. Empower them with large-scale maps so that they have this information at their land parcel level so that they can harvest water, they can drill water. And you would be amazed to know that based on these maps and follow-up survey on the ground, more than 300,000 borewells have been drilled in villages and hamlets. More than 10,000 water harvesting structures have been put. And we have feedback coming in from the states. And about 50 to 60% of the area being rain-fed, we have to ensure availability of soil moisture in the watersheds. We have to see that the productivity goes up. So ridge to valley kind of management of our watersheds. And we have the most innovative watershed-based or participatory watershed development program. In fact, this project has won many accolades. This is one example which was supported by the World Bank, being emulated in Africa, Sri Lanka, Bangladesh, and other places. And it is not that we try to give some maps or inputs for the planners at local level or different levels. We also use subsequently satellite data and monitor how actually the implementation on the ground has worked, in terms of water spread, in terms of increased agriculture, whatever. So now integrated watershed management is being extended to more than 48,000 watersheds across the country as a part of the federal government's program. And as I told you, we have nearly 120 major reservoirs. When you have reservoirs like this, you see our reservoir silting capacity or reservoir silting rate is 1.5 to 3 times higher than what we had planned when we constructed the reservoirs. I mean, again, the danger of being close to tropics, torrential rains, many a times, you can't control soil erosion silting. So we regularly monitor the upstream, the command area. We monitor the reservoir for silting and capacity loss. Then we monitor the downstream as well for reservoir operations. So this is again a part of National Action Plan. And we carry out, of course, performance evaluation of the command areas, whether the water release has resulted into the expected cropping downstream in the command areas, because this is extremely important. And you would appreciate that, 5 years ago, we were growing food grains of about 220 million tons. And all these innovative applications have led us to reach something like 260 million tons of food grain this year. And cropping area progression with the rainfall. I told you about monitoring of the snow basins, basically to study the snow accumulation, snow melt runoff. And all this data which we have been generating over the years now are organized into the web-enabled geo-portals or databases. In fact, we have a portal called Bhuvan. One can go to web and see. This is a public database. We make it available to all the authorized users in the country. About 90 layers of data. We have exclusive one for water resources, which is India WRIS portal. This is again having about 85 to 87 with about 7,700, more than 700 attributes. So all this is made available to all levels of planners up to grassroots level users. Thank you.
And finally, on space assets and the nexus of water, food, energy, and development, and more, Dr. Richard Lawford.
Thank you, Bob. Do I have to point this in a particular direction?
Yeah, no, it should work just fine. Jeffrey, can you help him with that? Can you bring up the PowerPoint for Rick? There we go. Okay.
Okay, thank you. So this is a brief overview of some of the issues related to fresh water. We've heard a number of examples already which elaborate on some of the perils that fresh water faces. For example, there's a lot of demand for water from development. The agriculture and food sector is a major source of that demand. 70% of the water that's withdrawn for use by humans is basically consumed by agricultural production. And it also is hungry for energy as well. A third of the energy that we produce is used by the agriculture community for the production and processing and transportation of food. So food is a big driver of water, and it relates to the population pressure. As populations grow, the demand for food increases, and often the population pressure is coming in areas where water is in short supply. There is also the fact that water quality is impacted by industrial and municipal waste and by the various activities that go on in a region. And on top of this, we have the effects of climate change, which lead to increased variability, such as the droughts we've been hearing about in California, and drying in other parts of the world as well, with other areas becoming more subject to floods because of the extremes that occur. By and large, it's projected that by 2030, that the demand for water is going to increase by 53% over what it was in 2010. And some of the largest increases are going to come in those areas where the water is already in short supply and people are already feeling stress because of their lack of access to water. So what is the promise of space? Well, we have a number of sources of Earth observation, satellites. We have the space station that are providing us with global maps and data for the globe on a periodic basis. We have networks of in situ measurements that provide local and high time resolution data. We are also developing data assimilation outputs and model outputs, which to some extent are being accepted by the community now as Earth observations. In order to manage the resources, though, we need other types of information. We need information that comes from surveys and what happens in households. Health and socioeconomic data are needed, and even in some areas, traditional information and knowledge is needed. Satellites have a number of advantages. They can provide geospatial consistency, which has not been available before. We've been hearing about the GRACE data, and is a remarkable development. It allows us to compare between countries where we weren't obtaining data, because some countries didn't collect the data, some didn't share the data, but now with GRACE we can estimate, although at coarse resolution, groundwater. And that allows us to do problem identification and verification. It also, through space data, it allows us to estimate things like evapotranspiration, and these can be used to monitor where irrigation water is being supplied. In the western U.S., in states like Idaho, for example, they're using satellite data now to assess whether farmers' claims are correct. A farmer may claim that they didn't get their adequate allocation of irrigation water, and they're able to go back and verify that claim or deny the claim, depending on what the evapotranspiration maps show. So there's a monitoring capability. A large part of the world is moving towards integrated water resources management, looking at water resources on a basin scale. The Nile is one example where they've been trying for several years now to do their planning and management, looking at the subbasins and looking at the total basin. But there's a problem because not all of the countries willingly share the data. And this makes it difficult when one country doesn't share the data with another to actually do planning. But this problem becomes a little bit obviated if we have satellite data that allows us to estimate what is going on basin-wide. Of course, we do need the in-situ data to validate the satellite data, but satellites do offer us an opportunity to move forward. There's a lot of discussion now about the post-2015 development agenda. And the World Health Organization and other groups like UNEP have been working on looking at how we might integrate in Earth observations to the monitoring of indicators, particularly for the Water Sustainable Development Goal. And the vision, admittedly, for some of these agencies is a little bit limited. But there's a task team that has been set up that is now advocating that we redesign these Sustainable Development Goal indicators to try to take full advantage of the spatial and temporal capabilities that satellites provide. For example, there has been a product that has been produced where TRIM data are passed over the vulnerable areas of the world where landslides might occur, and from that one can predict the probability of landslide occurrence. Suppose you were to take a map that, as this map shows, that gives the percentage of population that has toilets which are not connected to sewer systems. Those are problems because when you get a heavy rainfall in a lot of these countries that are yellow and green on this map, what happens is that the waste flows out into the streets and people get sick from diarrhea and other diseases. So if we're talking about sustainable human societies, particularly in these parts of the world, can't we do something by taking GPM data, precipitation data, mapping the precipitation that's estimated over a 24-hour period, identifying where these areas are, where it's likely that these problems will occur, and intervening in a way which will help solve the problem. Earth observations has a lot to offer, and I think all of us in this room see the promise, but there are some challenges that have to be overcome. And what are those perceived problems? Well, if you go to the water resource community and ask them why they aren't taking advantage of this data, some of them will tell you, well, it requires too much training. Others will tell you it's too difficult to change our routines and to incorporate satellite data. We don't know how good it is. Some of them will say the lag time between the observations and the data product availability, they're too long. We need to have the data immediately. And we don't want to move our system to a system where we don't have a guarantee that there's going to be continuity of the observations. So to really integrate Earth observations into society, we have to address some of these issues that people are raising. Now, a proposed path for this is to move towards more integration. One particular form of this is a water cycle integrator, which is being developed by the University of Tokyo, where they're looking at developing a data assimilation system which takes remote sensing data, in situ data, takes the model outputs from these systems and
One more
feeds them
minute,
into an application system, and this then would interface with the users, and they would be able to make use of the data that would be available. NASA's also contributing to this through the development of their land data assimilation system, which provides for the integration of satellite and in situ data and provides integrated products. There is also an organization which is setting out to address for the water societal benefit area this particular challenge. It's a voluntary partnership known as GEO, which brings together 90 national governments and 77 international organizations to develop some integrating public infrastructure that will connect these observational systems. And this may be a hope for bringing Earth observations more close to the users so that they will start using them on a daily basis in their decision making. But we really, I think, need to identify some new opportunities like the water, energy, food nexus and like the sustainable development goals for getting people to think in a new way about the applications of Earth observations to address our real world problems. Thank you.
Well, first of all, I'd like to thank the panelists for their tremendous discipline and staying in time. So I have one question for all four panelists, if they would choose to answer it. With regard to satellite-based observation of the Earth's freshwater resources, what do you think are the biggest breakthroughs that you anticipate coming in the next decade, and what are the greatest challenges? Jim, would you like to start?
Sure. I think that the biggest impact we're going to see in the next decade will come from the fact that we will have so many commercial satellites that are available and other satellite systems coming online that we won't have the almost over 2 week cycle time that we get back to look at the same area again. So we'll get much better coverage, which will lead to much better predictions. I think the accuracy of the new sensors and data that are coming online will also be an order of magnitude improvement from what we have today.
So I'm looking forward to the launch of several missions. The follow-on to GRACE launches in 2015. The NASA Soil Moisture mission called SMAP launches this winter. And the SWOT mission, the Surface Water and Ocean Topography mission, launches sometime around 2020. And so I think that it's an unprecedented era of satellite hydrology. And if we can integrate along the lines that Rick was talking about, we'll have a fundamental breakthroughs in our understanding of how water moves over and through the land.
Okay, you're all starting with the breakthroughs, so we'll do that first. Dr. Hegde?
I feel more and more countries or more and more planners across the world using spatial information coming from the satellite data would itself be a big breakthrough, because I think the synoptic data, the power of synoptic data is still to be fully exploited globally, which satellite readily provides.
Yeah, I'd just like to echo Jay's enthusiasm for the SWOT mission. We have had difficulty measuring stream flow and water levels, and SWOT offers an opportunity to address that. I guess just to add to what's been said, improved prediction capabilities relying on these inputs from Earth observations and satellites will be important. Integrating the space station observations in with the satellite observations into an integrated system would be a step forward. And in terms of challenges, bringing that user community together with the people who are supplying the data and ensuring that they understand how to use it and that we create tools for them to use it easily is a challenge that we need to address.
All right, I think all four of you have done a good job of demonstrating where the breakthroughs are going to be. What do you anticipate, Jim, as the big obstacles that you face in the coming decade?
So I think the biggest obstacle is the fact that we're data rich and knowledge poor. We have more and more satellites coming online with more and more data, And the ability, however, to get that data, convert it into knowledge, is a very, very difficult problem. The way we've attacked the problem in the past has been with very dedicated systems, very dedicated software. But what we've seen is that the way to attack big data is through making the data available and then allowing people to write their own apps or be able to take the data and put it into a form that people can use without a lot of training. How that comes about, I don't know, but I think that that's our biggest challenge going forward, is moving from data to knowledge.
I'd just like to highlight a few unknowns that I think are very important for monitoring and modeling water resources. One big one, of course, is that we really don't know how much fresh water we have on the land. We certainly don't know how much groundwater we have. So it's difficult to answer the sustainability question without knowing how much money is in the bank, so to speak. And, I could go on and on about the things that we don't know, but another great example is that we really don't have a global map of how deep our soils are. We don't understand what the topography looks like underneath rivers and underneath lakes. And these are all things that we need to tackle moving forward in the next decades in terms of improving our predictive capabilities.
I think the most accurate database which feeds into proper enactment of policies, especially in the developing world, that is an issue. I don't really call it as an obstacle, but that is one thing which should keep happening time and again.
Dr. Lawford?
One other challenge would be keeping the public's interest high in this field of Earth observation so that there is a sustained flow of funding that will help us solve these problems.
All right, the second question I want to ask, and it really flows from the first, and I think Dr. Hegde touched on it really actually directly. It seems that the biggest challenge facing those concerned with global water and climate security is that we haven't been able to penetrate our badly fragmented and highly territorial national and regional political systems with critical new understanding of the consequences of the disruption in the linked ocean, land, life, water, weather, climate system that's provided by space technology. We haven't been able to impose that fast enough to affect timely change. Would any of you like to comment on that?
I would love to comment on it because I work very hard on that very problem, and so it's along the lines of how I finished up my comments. We spend an awful lot of time doing exactly that, or I used to when I was at university, travel to Washington D.C. and talk to Congress members in particular in the Western United States, where water is quite a big issue, and the bottom line is that there's tremendous competition for their attention, and I could be in there talking about something that's extremely compelling, like the drought, and the person behind me could be talking about something that's equally as important, maybe education or some health issues. So it's an incredible challenge. I think we have to keep working at it. Beyond that, I don't have an answer.
Right, I'm going to let the other panelists answer that question, but before I do that, I would invite, if you have questions, perhaps you could prepare them. And if you could raise your hand, then we'll collect those questions for you so that we can answer it. Now, anybody else like to comment on this? On the question of making sure that we are somehow finding mechanisms to reach fragmented territorial, national, and political systems with this new understanding. I think it's a real challenge widely in matters related to water. I think for some of the reasons that Jay has outlined, other issues are more prominent in the public imagination. But as we see hydroclimatic shifts, then more and more of these kinds of problems are going to present themselves. One of the things that I should tell you is that in Canada, a recent RBC survey, the Canadian Water Attitude Survey, indicated that 10% of Canadians have experienced personally damaging effects of extreme weather events, and another 20% of Canadians know someone. So there are things happening here. Anyone like to comment further on this? Dr. Lawford?
I think that there's the crisis response, and probably governments are pretty good at that because they have dealt with it that way for many, many years. So if you have a drought or you have a flood, then they have programs that they put in place to try to help people who've been affected by it. But we have to move to being anticipatory and understanding how climate change will lead to greater variability, understanding how Earth observations can help us address some of these problems. And so redefining the problem and putting Earth observations into the problem, like water, energy, food nexus, for example, how do we use Earth observations effectively, changes the dynamic of the debate a little bit so that it's not just a crisis response, it's more a problem that we work together to solve.
Dr. Hegde, you seem to have made some progress in India on these matters. Do you want to discuss that? In terms of getting federal governments and other organizations to move toward national strategies.
Yeah. See, basically in India, the success of our space application program can be attributed to a virtual system called National Natural Resources Management System, which is a virtual body spearheaded by the Federal Planning Commission, where all the ministries concerned with the development, all the state government departments, even private industry, academia, everybody forms one virtual organization. So the national imperatives drive us to develop and implement certain kind of applications. But still, as I told you, see, a simple example of across one river which flows, say, thousands of kilometers, say there are 5 reservoirs. If there is rain in the upstream and one reservoir gets filled up, how much water you utilize in the immediate command which is next to it, or how much water you release to the next reservoir, the question is the people come in, the political system comes in. So that is why I told, ultimately we have to succumb to the power of synopticity, the total water available, how much of water allocation one would do for which part of the basin, which part of the river basin. I mean, see, we don't have much control on, how much water is received as input in your territory, in your region, or in your country. Because those things, one can keep on doing a lot of research, though it's very important. But managing water absolutely at ground level and keeping your population happy, citizens happy, becomes a critical issue. So I think in India today, all the departments, whether in the federal system or in the state system or down below, appreciate the value of synoptic data coming from the satellites and try to use it to the best possible.
All right, we have just a few minutes left. Jim, do you have any comments on that? No? Anybody else? All right, we have just a few minutes left for questions. Are there any questions that you might like to ask from the floor? And please understand that none of us can see anything here because the lights are so bright, so if you could bring the questions forward for us. If there's any questions you may wish to ask? Well, that being the case then, I don't see anyone who wishes to do so. What I'd like to do, is there? Oh, right here, please. Oh, okay, here we go.
All right, so you've all hinted on the importance of temporal resolution for all this. Have you ever considered using small satellites that are obviously cheaper and hence you can make more of them, have much higher temporal resolution with them, but of course they have limited performance?
Do you want to aim that at any individual panelist or just everybody?
Whoever wants to take the question.
So I'll start off. Sure, smaller satellites can be more cost effective. We can get things at higher resolution, and we have programs within NASA to propose those sorts of things. There's a lot that we can do. It's just a competitive funding environment. So I wish we could do more.
So satellites should be as small as possible, but not smaller. I think that's a quote somebody made. And the two competing things for this, I think, are Moore's Law. As electronics get smaller, as sensors get better, there's a lot more that you can do on smaller satellites. And so we're seeing that, in fact. It's a kind of natural evolution On the other hand, on the other side of it's physics. There are certain aperture sizes that you need to get certain amounts of data. So small sats and microsats, small sats, don't solve all of the problems that we need to solve. You know, part of this comes down to funding at the end of the day, and it was said earlier, I think all of us need to do a much better job of communicating to the policymakers and to the public about how important this is. I used the example of the apple earlier because the fact of the matter is we think water's not a problem, and it really is.
I'd just like to comment, working principally in water, and I know that others on this panel do also, but it appears to me that water is the very central element of what climate change actually means and how it expresses itself. And it also, I think, based on the comments of the panelists, that it's pretty clear that water security is a major issue. And I'm really glad that Jim brought up the issue of funding for programs like this and ongoing support for the types of scientific connections that are being made. So are there any other questions that others would like to answer? All right, then. Oh, there is one. Okay, please go ahead.
Sorry, I'm at the microphone. I'd like to ask you how you link some of the measurements you have mentioned with the measurement from missions at SMOS, satellite, measuring moisture, salinity, as well as Cryosat, looking at the cryosphere, and the European program for global monitoring of environment and security, because you didn't touch it too much or not, or are you blind to what is happening in Europe, or how do you integrate measurements from Europe? Thank you.
Okay, I'll go first. No, we're not blind. We do, so I think the best, so there are two ways in our group that we tackle the problem. We use multiple sensors to tackle global problems, and of course, you know, we know all about the various missions that are out there. I've been following SMOS, for example, for a long time. So we analyze the data independently. We combine it with other satellite missions. But then, as Rick mentioned, you know, there's a big need to integrate the data into models to sort of get this full understanding of where all the water is and how it's changing over time. And it again, we're funding limited. It takes a long time, but our eyes are wide open.
Anyone else care? Dr. Lawford, please.
Just to comment on that, there's a lot of interest within the global Earth observations community to bring together those types of data sets, and SMOS has made remarkable progress in terms of reaching out to communities of users and getting applications underway. And to a large extent, that's facilitated both by ESA's interest and by the European community's interest. And one doesn't want to minimize the contributions of the European Commission to doing research in the water area. They've done a lot over the last 5 to 6 years, and a lot of the developments for the group of Earth observations has relied on the European Commission. So if you didn't hear the European Commission or Europe being lauded for some of its achievements, please don't take that as a view from this panel, because we really do appreciate their efforts.
Okay, thank you. Mm-hmm.
I have a question.
Yes, well, one last question. Please go ahead.
Now that it's increasingly likely that the International Space Station will be available till at least 2024, are there other sensors or measurements that we should be taking from space station that we aren't doing at this point in time?
So I would say that that's definitely true. One of the things that NASA is trying to do now, that we have routine cargo flights to the space station, is to identify instrumentation that it can actually be brought up at, of course, lower price, because you don't have to launch a dedicated spacecraft to do it. And there's been a number of proposals to do that, and I think it's quite possible that we could see instruments brought up to the International Space Station. Now, with that said, there's a lot of limited coverage. You don't get a polar orbit. However, for certain types of observations, that's certainly a reasonable platform to perform it from. But it comes with challenges as well.
Okay. All right, well, our time is coming to an end, and I'd just like to summarize some of the remarks that were made. And this is truly a remarkable panel. Jim Crocker reminded us that the Earth is not flat, it's round, and it's covered with water, and that space technology allows us to see the world differently, to determine subtle but real changes such as algal blooms and other contaminations. And he gave many other examples of how satellite observations can help us detect things that we might not be able to detect ourselves. And he's noted also that satellite observations have become more accurate and timely, and that new instruments increase our reach. Jay focused on groundwater as a strategic reserve critical to water security. He explained the gravity recovery and climate experiment, or GRACE, especially in the context of, and the unique context of current water crisis in California. I think he really did something that's very important that needs to be done in public understanding, which is to dispel this myth that groundwater and surface water are different. They're really the same thing, and he showed us that those water resources are definitely connected. Demonstrated the trends of unsustainable use, important agricultural regions to which we must pay attention. He paraphrased Einstein by said, "Those of us who have the privilege of knowing have the duty to act." And I think sometimes we stop short of that. When we have the knowledge, we aren't as effective in sharing it. Dr. Hegde used space technology to demonstrate how it could be applied in very, very difficult water shortage situations, small geographical areas, limited water resources, and huge population. He also pointed out the importance of accurate snowmelt monitoring and prediction, critical in the Himalayas certainly, but everywhere in the northern hemisphere and southern hemisphere where water resources are principally coming from snowmelt. He also outlined the importance of groundwater mapping to water security and the importance of tying outcomes into participatory watershed development in the larger context of integrated watershed management. And I think in many ways, India is ahead of many much more developed countries in terms of doing that. Dr. Lawford outlined the water needs associated with development, and then went on to outline the promise of space in combination with in situ Earth observations. He then discussed data inputs into decision-making process. And he also brought up the challenge of linking data and sharing data in ways that inform decision-making. And he also noted that this was critical to achieving our sustainable development goals. And Earth observations have great promise, he said, but only if they're used. Integration of products is critical, and it's one thing to have satellites and satellite data, another to ensure that users possess the information they provide and act on it. Finally, the breakthroughs were faster cycling times of satellites, which all of us, I think, benefit from. Improve accuracy over a broader range of parameters, new missions, better data sharing, and improved prediction. And I think the obstacles that were outlined were critical, and I think they show the direction that science in itself has to go in terms of dealing with hydrochromatic problems. We are data rich and we're knowledge poor. Our biggest challenge is moving from data to knowledge. We still need to know very important fundamental things. How much water do we have in the world, and where is it, and what's it's doing, and what it's doing. And the other problem is using that data unequivocally to inform public policy. And it was also noted that keeping public interest so that the public can see value and can see immediate benefit from this very high technology that's being employed, so they can see that it means something to them. So the challenge is being anticipatory, trying to move ahead on a consistent basis, an informed basis, and not being affected by only emergencies. And I think, as Dr. Hegde pointed out, it requires the focusing of federal interests in water security and tying water security to development and to Earth system function and sustainability. And I was grateful that Jim Crocker brought up the issue of funding, because it is a critical matter, the consistency and overall pattern of funding and support we have. And also tied to that is that sometimes that's very hard when our water systems generally in North America, for example, are very good, and therefore the myth of limitless water abundance prevails oftentimes when we know scientifically that that's a very tenuous proposition. Finally, though, I think it's really important to note, and I think it's as Dr. Virendra Jha pointed out in an introductory call to the panelists, and And his point was this, and I think that this panel clearly reinforced this point. There is a problem, a very real problem out there hydroclimatically, and space offers hope to solve that problem. Will you please join me in thanking this very distinguished panel?